So I guess it's time to begin. Our next speaker, you all know already, Ken Oldham from Mechanical Engineering Department here. Before that, I think you were at Berkeley, right?
Yes. Yeah.
I think you're in the Mechanical Engineering Department.
Yes, yes.
Yeah. Okay. And he works on a really wide variety of interesting control applications, and I'll let him.
Yeah. Thank you. Thanks for having me. So can the folks online here? This is a couple, but is the microphone working? Are you folks thinking? Oh yeah, because it's going up on the top. Yeah. Yeah. Okay, good. Thank you. All right. So thanks for coming, everyone. Thanks for having me here. So I'm going to talk, as the title says, about control applications to microsystems-based endoscopic imaging. And so I'm not going to claim that these are going to be particularly complicated control sorts of applications, but they're ones that you might not encounter so much outside of microsystems-based engineering, or maybe haven't thought about how they could come into other scales, be used in other scales. And I think it's a pretty interesting application. So I've been working for many years with a team of researchers studying something called microendoscopy or endomicroscopy, depending on how we feel at the day, the time of day. And this is really a big collaborative work across a bunch of folks in engineering and medicine and other departments. These days, it's been wrapped into a new NIH Center on Microscope-based imaging system with some of this is just a partial list of the folks working on it with us, but in particular, the person on the left there is Thomas Wang from internal medicine and biomedical engineering and mechanical engineering, who I've been working with for a long time on these systems. And I'm going to spend some time introducing what this microendoscopy concept is, why it connects to microscale engineering, and then where control can come in or not to using these systems. And so let me start off at the beginning. So folks are most likely familiar, or at least have heard of endoscopy. This is, broadly speaking, endo just means inner. So any sort of tool that can be used inside the body, usually by a minimally invasive insertion, but most commonly that means imaging in the esophagus, the gastrointestinal tract, and the esophagus or the colon. And so this is a very common tool for disease diagnosis and intervention. Various diseases, Tom particularly works on cancer, and most of our collaborators work on cancer, but other diseases as well. But there's this particular problem with cancer that promotes a lot of this work, which is that, yes, if there are symptoms or just from regular screenings, doctors will do imaging inside the gastrointestinal tract, looking for polyps that are potential indicators of cancer, but about 25% of polyps appear as flat lesions on the sidewall of the organ, and those are easily missed. And there's considered to be about, for example, in colorectal cancer, about a 25% miss rate if you're just doing white light imaging. And a typical endoscopic tool doing this, well, the actual endoscope is fairly large, a few centimeters in diameter, but it has multiple what we'd call instrument channels. And each of these can bring in a different function. One of those is this white light imaging. And so when I talk about a microendoscope, I'm going to be talking about one of these tools that would be introduced through these channels or otherwise into a human or animal in order to do in vivo imaging. Closely related to tools like laparoscopy, where you make an incision to insert a tool to image a given space as well. And so there's overlap between these domains. So if flat lesions are a problem in white light, one of the potential solutions is to use fluorescence-based imaging, and particularly fluorescence-based microscopic imaging, meaning resolutions down to few micron or so scale. Regular polyps might be very easy to identify in the gastrointestinal tract, but flat lesions, it's not impossible to tell where they are, but much more difficult. And these appear much more brightly if you can apply a fluorescence biomarker and then detect fluorescence emitted by that system. So a lot of work that Tom does is on molecular probes that preferentially bind to cancer tissue and bring a fluorescent molecule with it in order to be detected in the optical instruments. There are systems to try to do fluorescence imaging already. For example, something called a scanning fiber endoscope, where you send a single fiber into the tool and bring it into resonance so you can create a spiral or other scan pattern that will collect an image, or confocal fiber bundle microscope where you have a whole bunch of fibers coming down in a single instrument and each one individually focusing on a single spot to collect an image, and then some fancy image reconstruction filling in the best estimate of the rest of the picture. Big difference between this and the white light imaging is you can see this is all being delivered by fibers, because we have to excite the fluorescent effect, they have to focus the laser on the space. In most cases, there are some exceptions. Mostly you want to focus the laser into a very finite high resolution spot and then collect the fluorescence emitted from that same location. So these tools exist. There are a couple limitations to them. One of them is that they only really image on the surface of the tissue. The image, and we do instruments that do that as well. We do instruments like the single axis confocal imaging, where laser is focused on a single point in front of the instrument. We even do much coarser resolution, wide field imaging, where we scan a laser across a large area of the internal organ. But the more novel designs developed in the imaging center are related to deeper into tissue imaging. Now, deep is not necessarily that deep. We do things like multiphoton imaging, it's called, or dual axis confocal imaging that are purely optical modalities that are capable of penetrating a few hundred microns, half a millimeter or so, into tissue and collecting fluorescence with sufficient rejection of scattered light to collect a usable image. And then we even move into mixed acoustic and optical techniques such as photoacoustic imaging, where you can go much deeper, but again, at a very low resolution. And so we do a lot of work on trying to scan laser light through really 3 dimensions of tissue space in order to build up an image. Again, none of these tools, by and large, are being researched all in different places in different ways. Main exception, dual axis confocal, is not done very many places besides here at U of M. But tools of these types are under development many places. And so the other thing that was kind of different about how we approach this is our use of microelectromechanical systems. And so micromechanical systems are really sort of my core area. Dynamics and control of these systems usually. If you aren't familiar with these, they are essentially, you can think of them as silicon chips with moving parts. Each of these micromirrors shown up here consists of a chunk of silicon that was originally part of a silicon wafer, some rigid portion that we've covered with a reflective surface, and then, or sometimes 2 reflective surfaces, and then actuation systems around in one or more various configurations around the device in order to drive motion. And so this is beneficial in these miniature imaging systems relative to some of the purely fiber-based methods we talked about, I mentioned before, because often they can achieve wider field of view, larger scan angles, so a larger imaging space. By doing the scanning very close to the distal optics, you minimize optical aberrations versus some electronic scanning techniques one can do from hardware, from earlier in the imaging process. And we can put all of the scanning motions in some cases in a single devices that can do scan axially, change the depth of the scan, and back and forth in 2 axes to build up an image. And so this is the hardware, various actuators this type. I'm going to talk about some of the controls issues that come into play over the rest of the talk. But before I do that, I'm going to talk about what goes into the design of these, because that dictates what we have available and what problems we face when it comes to control. I showed just a variety of mirrors that happen to have good videos on the last slide. But in most of the time, we rely on 2 main actuation schemes for our devices. One is called parametrically resonant electrostatic scanning. Just in general, when you shrink down to the micro scale, the amount of energy you have available or work you can produce from an actuator becomes quite small. Most of the time in microsystems, you also want to scale down the size and inertia of whatever you're moving or so forth along with it. But micromirrors are going to put some limitations on that, as we'll see. So you get around that a lot of the time by operating in resonance. And in particular, parametrically resonant scanners are built as planar systems that can only operate at resonance. It makes them very simple to fabricate. It gives them a high resonant frequency, but it ends up with some nonlinear dynamics. And again, you can resonate it or you cannot resonate it, and that's what you have available to scan the laser light. The other types of systems we work a lot with are thin film piezoelectric actuators. So piezoelectric devices, if you're familiar with the macro scale, you apply a voltage across them and they contract or expand. At the micro scale, there's thin films, thin a micron thick film across a wafer. They contract and they naturally produce sort of bending motions because they are contracting relative to the neutral axis of other layers in the structure. So instead of sort of the parametric resonance scanners use sort of attractive forcing between an array of fingers that are moving back and forth on a chip. Piezoelectric devices rely on bending beam elements that are distributed in a way you think will provide useful motion on chip. These are about the highest energy density devices you can have in microsystems, not the highest, but quite good. Because they have much higher energy, you now can do both static and resonant displacement, which will come back late in the talk, and operate over a wide frequency range, but they're much more complicated to fabricate and assemble into these systems. So these are the two main types of devices we work with. And so if we are trying to set up a new scanner for a new endoscopy system, we basically have to balance the limitations and capabilities of the scanner with what the optical system needs to provide a useful image for some clinical or scientific task. Generically, what's happening in one of these devices is there's a laser source coming from outside the instrument. And it's coming through a fiber. It reaches the distal optics that might be a few millimeters diameter and a centimeter or two long. And there's a series of lenses to focus that light. And then somewhere in the lens path, and there's various ways of setting this up, somewhere in the lens light path, there's a scan mirror that's at least rotating in one and usually two axes so that you're scanning your laser point in 2D space to build up an image. Maybe that's 2D horizontal image, maybe it's a 2D vertical image if you have that depth control, but you're scanning in 2 dimensions to build up an image. From an optical standpoint, from an optical design standpoint, basically with any of these modalities, the more you want the better resolution and the better field of view you want, the better your actuator has to be. So it makes sense that you have to get something, you need a good actuator to get a good optical performance, but it's really quite direct. This NA here stands for numerical aperture. Field FOV stands for field of view. The numerical aperture, which describes kind of the cone of light that's being illuminated, is generally directly related to resolution of a given imaging modality. And the field of view, of course, is how big your image is. That product scales almost in a not linear simulation, scales almost exactly linearly, and in a more realistic ray trace simulation, close to that linear trend, with two metrics for the mirror's use, which are basically the size of the aperture, in this example, the minor radius of a elliptical reflector, and the tilt angle that scanner can do. So upshot is your best optical performance is gotten if you can make your aperture as big as possible and your tilt angle as big as possible. Okay, that makes sense. And these particular examples come from work on an implantable 2-photon mirror microscope developed by these students, my student Tayaba and Ahmed Shirazi from the Wang Lab a few years ago. So we're approaching this and we're like, okay, we want to make our reflector large, we want to make our tilt angle large. From an actuation standpoint, usually those work against each other. The larger we make the reflector, the less we're going to be able to move it, usually, back and forth. And so we will have to conceive of some actuation model for the system. In these parametrically resonant devices, where you have a electrostatic attraction between some comb fingers on chip, and it's causing say a mirror to rotate about an axis. The mechanics of the structure really looked like just a mass spring damper system, a torsional mass spring damper system, but a spring damper system. And then the motion is driven by electrostatic forcing, which can be described by the derivative of capacitance of the system with respect to the angle of displacement, so, or the axis that you're interested in. And so we will take a hypothetical mirror geometry, attach comb fingers to it, and build up a model of capacitance versus angle. This is, for example, this is a both a basically numerical approximation and then a Gaussian approximation of the tilt angle of the capacitance versus tilt angle for a sample mirror. And then we can use various dynamics analysis techniques to project what the amplitude of vibration will be at a given input. Usually we put this in dimensionless terms first so that we limit the parameters, usually to the damping ratio. There's a nonlinear term, so there's a parameter related to the nonlinearity of a Gaussian model, which we find works well in a lot of cases. And then we have conditions such as, and then we also have a scaling factor between the nonlinear and nonlinear amplitude and the absolute amplitude when we're trying to evaluate performance. And so we can analyze all sorts of nonlinear dynamics, but from a design standpoint, that is 1/2 of the equation because it tells us, well, so far it tells us if we put in a voltage, we get a certain amount of motion. But we also have to couple this with some sort of failure model. So we also try to identify what's going to be the limiting factor for a given device. For this particular instrument they were working on, we had a mirror that was intended to be roughly elliptical. And it's rotating back and forth in 2 axes. And the limiting factor is that these comb finger arrays, they're attracted to one another. And if they move into unwantedly off axis, they will crash at too high a voltage. It's called electrostatic snap-in or pull-in. And this is a device where that's happened. It has arced current where the crash occurred, spewed metal all over the place. That's all these particles we see, and that mirror is not going to work very well. So we do some modeling of what's the internal deformation of both the fingers and unwanted rotation due to the compliance of the structures that hold us up, and we come up with some sort of limit on what voltage you can achieve for a given nominal geometry in this case. In a piezoelectric mirror, it might be a limiting factor of what's going to break down the piezoelectric material or what's going to physically fracture other layers in the stack. And combining these together, we can try to optimize some other imaging criteria. So we have a constraint we already know we're trying to push. One is to simply push the tilt angle times the aperture size as far as possible. If we know that we have a certain aperture, certain field of view target, then we might optimize a secondary criteria, which, for example, in this case, was frequency. We knew we needed for a given application about a total of 5 mm aperture angle product, and about the highest frequency we could project to was maybe somewhere a little above 4 kilohertz, 5 kilohertz sort of range. And that's how we kind of came down to a given design for this example. And so here's one of the finished mirrors from this device, from this process used in this multi-photon imaging system. Again, it's a non-linearly actuated system. So in fact, you'll see a bunch of softening dynamics in this particular case, something called electrostatic softening. And then we can plug it into a given instrument. This is a benchtop test where we're imaging neurons and mouse cortex, collect images of some fluorescent bead phantoms, some neurons dyed with green fluorescent protein at a depth of about 250 microns over about a 500 micron by 500 micron field of view. And that's really quite good for an endoscopy system to be able to go that deep and have that wide of a field of view. So that's nice. That works. It works pretty well, but there's several things that might make us want to use control. One thing, if you were looking at the last slide and noticed it, the modeled frequency response of the system was well off the experimental frequency response, shifted by about 10% in frequency, in fact. And that's not unusual for our ability to control the fabrication processes behind these devices. And what's more, as you perturb the environment due to temperature changes, humidity changes, even aging of the devices, we get further shifts than the natural frequency of the device. And that's quite bad for imaging registration, as one might imagine, or we'll come back to in a second. We also are trying to drive these usually in multiple axes at once. And that analysis was one axis at a time. Most of the time, our analyses are one axis at a time. But once you get multiple axes moving, most devices end up coupling together in better or worse sorts of ways. And that introduces more challenges for control. More reasons you might want to have control. On the other hand, at this point, the biggest message has been, for the most part, you want to use as much of your chip area as possible for the reflector and the actuators, because that's what's going to drive your optical performance. And we rarely have a space available for much sensor feedback. Not just because it takes away from space we might use for actuation, but because it means additional electrical connections on chip, and that is a space budget that takes extra space as well. We rarely like to afford to spend the effort or the space on that. Operating frequencies are high, at least these look for, at least relative to most large scale systems. Resonant frequencies are typically in the few kilohertz range and sometimes into the tens of kilohertz range. And by and large, our electronics are not built into the distal end of the endoscope. They're back at some control station, which means there's actually significant transmission delays relative to the size of the chip between the electronics and the actuator that we're actually scanning with. And so I'll spend the next part of the talk basically talking about different ways we've tried to handle these sorts of issues. All right, so one of the ways we try to deal with uncertainty in the system is just what can we learn about it just from what we're getting back as images? Even if we don't have any, if I was doing a typical motion control problem, I would want to have a sensor on my actuator that's measuring, say, tilt angle as a function of time. I've just said, usually we don't want to take the space budget for that, but we are still getting some feedback. It's really a record of intensity as a function of time. And this is entirely how we're supposed to reconstruct the images of our devices. With purely resonant devices, it's usually very difficult to separate a fast axis and a slow axis frequency very widely. So if we think about normally imaging in like a raster scan pattern, most of the time that's not what we can use. Rather, we use something called list-view scanning, where you have two separate frequencies. You detune the frequency ratio and the phase and adjust the phase so that the overlapping 2D coverage of the two sinusoids eventually fills up and covers the entire imaging space. And so as this is happening, you're continually getting a series of intensity measurements as a function of time. And then based on your knowledge of where your scanner was pointed at a given point in time, you register that pixel back to the point in the image. It's just single pixel imaging when you are using a single light beam to do the illumination. As this detunes, because of uncertainty about the properties of your system, it fortunately does so in some predictable ways. You're putting some in either axis, you're putting in some voltage signal with an amplitude, a drive frequency, and a desired and a phase angle that you control to try to create a desirable list-view scan. And then you're getting out a whatever angle of the system you're getting. Roughly the length of the angle gives you the field of view D. And then it's at if it's nonlinear force, it may be at a separate frequency with your intended phase angle plus whatever mechanical phase angle dynamics there are in the system or electromechanical dynamics of the system. If you know these perfectly, you're good. But in practice, there's some perturbation added on because we don't know these. Even if we calibrate it on the benchtop before we go into an organism, go into animal model, say, it will drift and change enough to cause image blur. It does so at least in a predictable way. Because it's using that list-view scan pattern, it means that it spreads out copies of the high intensity portions from their true sort of position. And so another one of my students, Meyer Burla, a few years ago, decided to apply some of the image processing metrics from autofocus world to this problem. He looked at a couple metrics for characterizing the quality of the image. One in the bottom is a kind of variance metric that's actually for used fairly often in autofocus. And another one is an older one on, you threshold the image and then calculate its blur based on the number of white pixels, which is not generally super popular, and as I understand, in autofocus anymore, because it's really hard to set the threshold. But because we know kind of how these images deep tune, he found that you could actually set a pretty reliable algorithm for doing this. And so he actually prefers this blur metric. And we tried this out on simulated detuning of a Lysidue scan over all sorts of endoscopic and just test images. And what you find is that you get, particularly with the blur image, you get a very, if this is actually the true phase delay in this particular in the simulation you ran, you get a very sharp detection of the true phase angle of the system based on this metric. Now, it's not necessarily perfect. You have many other local minima that can cause issues. But you need a very precise measure of the actual phase delay in order to reconstruct the image. And so this is what he began. So this is what he identified as a really nice tool for it. Variance metric works as well. They're not quite as sharp at minimum. So as long as you know you're in a rough range of what the phase delay should be, you can zero in on the exact value to sort of a sub-milliradian phase delay. That part's still covered up. Better up here, down here. And so this works very well, and this is something we actually do use fairly regularly. Go ahead. I think there's a video on the next screen showing this, and my computer's maybe not entirely happy to go there. Okay, here there is. So this is a simulation. Well, this is a data set. Sorry, this is not a simulation. This is real data where Meyer and one of Tom's students are working on imaging in vivo in a mouse model for cancer, and they get a brief enough image that's good enough they can run this algorithm on, very blurry. They run it. This was early, so it wasn't particularly fast. And then once they've identified this phase, they can bring in pretty well focused images as they move the probe around the colon of this mouse. And so we use this these days quite a lot. And we've played with other extensions. You can see that there's a lot of blur anytime you're moving the instrument. Play with the extensions for trying to track changes, track the motion aberrations with this as we go along. They work well in simulation, though in practice, the motions are too abrupt even for doing that, although Do and Tsai, one of the other members of the Imaging Center, is working on that as well. And so this has been very handy to us. We don't need to add any sensing to the system. It has a metric that is very well suited to the Lysidue scan pattern. And we can even extend it with things like Cowan filter for motion artifact to some extent. Of course, like I said, you have to have some prior knowledge of where your scan angle, where your phase delay was to begin with. I mean, you don't have to, but it works best if you do. You also need to have a decent quality image to do it. You have to know that at one point you are collecting enough signal to do the calibration essentially. And it really doesn't tell you much about motion amplitude, or really the big question for us a lot of the time is the mirror even still working inside the device? So even though this works a lot of the time, we've been wanting to go beyond that with more ability to directly sense the motion of the mirror, even though we're really reluctant to spend extra wiring or sensor device space on that task. And so the next thing we spent some time on over the years has been doing on-chip sensing, but using the existing capacitors that are present in the system. And again, this is another thing that's that is done reasonably often in microsystems engineering. These are various scanning mirrors of type. Again, there's these comb fingers moving past one another. The attractive force between the mirrors is what's driving motion when you apply a voltage, but it also means the capacitance is changing sometimes quite a lot while they move. And so if you can measure the capacitance on this system, you are ostensibly measuring the tilt angle at any given point in time. Now, measuring capacitance is not as easy as measuring some other things like resistance or so forth. You have to apply an AC signal. More importantly for us, even though the motions can be quite big, the absolute capacitance relative to other capacitances in the system, the capacitance change relative to other capacitance systems is small, and signal to noise ratio is pretty crappy when you try to use these as a sensor. And there's another phenomena that is really widely encountered in microsystems, which is called feed through. You're driving this sensor, you're driving this actuator at a given voltage. That's capacitively coupled to the sensor just purely electronically. So most of the signal you're often getting out is the coupled driving signal, not anything related to the actual motion. And these are widely known problems for us in MEMS engineering. There's just a few twists on these. I'll talk about how we deal with them and just a few twists on these that come into play for our endoscopy application. Now, so speaking on the poor signal noise ratio point of view. So one of the things is we have our capacitance versus angle models. They're not particularly perfect. And then as the finger moves through, you get a certain sensing signal that, well, the real thing somewhere in this big noisy thing, and then it transitions again. And you don't have a perfect model of that capacitance. You can do a okay estimate of angle versus time with this. But one thing we recognize is you do have one sort of ground truth to this, which is that you can be pretty darn confident that the absolute maximum capacitance happens when your fingers are completely overlapped. And so this gives you a single point in each cycle where you have a very high degree of confidence and a relatively steeper crossover in the signal on which to make measurements. And so another of my students, E10, working with engineer in Thompson of Mickey Lee, they first found that to pull out an even better estimate of that crossover point, they could feed this through a derivative of Gaussian filter and pull out a peak time from the derivative of Gaussian filter on when the crossover occurred. And then we built this into what we call a threshold Kalman filter, really more just a certain variety of hybrid Kalman filter, where most of the time you have your model, it's imperfect, running an estimate of the states of the mirror, position and velocity versus time based on that really noisy sensing signal. And then the derivative Gaussian signal is sensing out an occasional update that, oh, we crossed a high confidence point at this time, and then you're going to insert a essentially very well-known state estimate with very low variance on that noise signal at that instant. And it actually helps quite a bit. When we're tracking, here E is tracking signal at various amplitudes. And especially as you get down to lower amplitudes where the signal to noise is getting worse and worse, it's correcting the tracking of the signal at least near the threshold crossing by like several milliradians better than the standard, just a Kalman filter without that threshold. Yeah.
How do you get amplitude information out of that?
So you do get amplitude. Well, the amplitude information is there. Like you're
just measuring the zero crossing.
But we're not just measuring the zero crossing. We're measuring it all the time. We're measuring this noisy measure of capacitance all the time. Most of the time, most of the time, there is a change in capacitance in the background.
Oh, I see. So this is basically on top of that.
On top of that, you're throwing on the threshold detection. And it provides a substantial local improvement both to the amplitude, but even less important to us is that phase angle information anyway, phase delay information, I should say. So we're kind of getting both out of it. We're getting a good measure of that phase delay, which is most important to us, and it does help correct. It does a little bit of work to help correct the amplitude, mostly because it's interacting with a model that's not perfect, but is there to help support the measure. But even this is a sort of cheating demonstration because the other reason, not just to manipulate the amplitude, is this decaying. It's decaying because we are basically turning off the input voltage so it's not contaminating the signal while we're making these estimates. And so, again, this idea of feed through where the driving signal is directly coupled to your sensor output happens a lot in these microscale devices, and it's handled. We handle with modulation. So we run a drive signal that's driving the actuation into our device, and then on top of it, we piggyback a very high frequency or ideally a very high frequency carrier wave that the output voltage, the output oscillations have a portion that's proportional to the driving frequency at relatively low frequency. And they have a portion that's at the high frequency. And the portion of the high frequency is being modulated by the angle of the device or the displacement of the device. And so that's how we would often say separate driving and sensing signals in an accelerometer or a gyroscope, a MEMS accelerometer or a gyroscope. Basically try to embed the actual motion at the carrier wave amplitude, the drive signal at a much lower frequency, run it through a high pass filter, and then you can either do a demodulation circuit or simply an envelope detector here and pull out the signal that you think is due to displacement. And so this is one of the big limitation we ran into with implementing this on our endoscopic devices was the transmission line delays. We found that the amount of the bandwidth over several meters of transmission line to our sensors is disappointingly only in the few hundred, sort of maybe 700, 800 kilohertz sort of range, where we're actuating in the tens of kilohertz. And that's not nearly as much frequency separation as we would usually like to see for a demodulation scheme. And so we went through a whole thing of optimizing what is the best carrier frequency to balance reduced coupling in the drive signal and most we could get out of the carrier signal. It helped a lot. We could reject a lot more of the feed through and get a lot closer to the inferred real motion signal after this. Not perfect, but good enough. It gives us some amplitude information, good enough to get back to really clear phase information in Mickey's work. And again, be able to, based on the on-chip sensing, while you're running the driver now, estimate at least, this doesn't work as well for amplitude now, but it at least gives us that phase delay portion. So assuming we're getting a decent amplitude, she could correct this and resolve what was initially very blurry based on calibration of the mirror, and then based on the new phase estimate of what was happening, get a nice clear image of biological tissue. Yep.
Are you saying that that you're doing all the demodulation circuit and all that stuff is actually done off chip?
That's right.
So
Yeah.
It's like one op-amp. So is real estate really that expensive on the chip that you can just put it on there? Because
well, so it's more that a chip without that is cheap and a chip with that is extremely expensive.
I see.
Yeah. So yeah, but yeah, so to do that on chip, you have to have what we would call a CMOS compatible process. And those are getting more and more common in the MEMS world. But for one thing, this is all electrostatic. So you could do this in a CMOS compatible process. But like my piezoelectric devices, they're not CMOS compatible, both because of the materials and the temperature used, for example. And so, yeah, there are folks. So would you ever do this? I'm not sure. There may be at some point where it becomes cost effective if there's enough of these things being produced to do a CMOS integrated sensor. On the other hand, usually these sorts of endoscopy probes are actually not used for that many patients. I think of them as a durable device, but they're really not. They do like 10, 25 patients with them and they're done. So I don't know where in the long term one does this, but there are benefits to being able to do this without putting any of your processing hardware at the chip itself. No, that's a really good question. And so yeah, so this is another, that's sort of the other fairly well-developed area of control that we've applied to these systems. The third topic I'll talk about is just much more preliminary work. Up to this point, I haven't been willing to put on chip sensing. I've been talking about these electrostatic scanners but I mentioned that we have these piezoelectric actuators as well. The electrostatic scanners are purely resonance. They're always just working with resonance dynamics. Piezoelectric scanners have this ability, have enough work density on board that you can take a relatively stiff device necessary for high frequency scanning and provide enough actuation force to give it substantial DC offset. And so that allows us to potentially implement something called random access scanning. It also potentially frees up real estate due to the higher work density of the devices. Random access scanning, as we use the term, is to say that you have your instrument at a fixed point in space with some sort of scan, listed view or raster scan, you've got your full field of view. And then you direct your scan to a specified region of interest within that full field of view. And its benefits are somewhat like the benefits of optical versus digital zoom. In particular, if you're doing a listed view scan in a given frame, the truth is there's usually a lot of missed pixels. If you were to try to digitally zoom this by just going in a specific area, you could try some image reconstruction things, but fundamentally the information is not there. If you instead move your scan pattern and narrow it so that it's scanning that region, you are much more densely scanning over the area, fewer lost pixels, or probably more important for us is not so much pixel loss or even improving resolution, but to get multiple scans in a certain period of time so that we can do signal averaging, because some of these fluorescent signals can be very weak. And so we believe we can push up signal to noise in these devices quite a bit through this scanning technique. Or in things like neural imaging, just take frames faster because you can complete the scan in that region in a much shorter time. And so another of my students, June, has worked a lot on actuators to do this style of scanning. Actuators that might bend slowly out of plane in one direction and then resonate in the other so that you can, this is more like a addressable line scan back and forth. Or actuators like this, which can take an inner actuator and move it up and down so that you can basically slowly up and down so that you can get that vertical section, then move to specific points within it. Other folks that I work with, Yue and Hangji, worked on some of the controls for this. And we've done some demonstrations of this. This is just some basic wide field imaging of sort of these random access scans. So June is holding his system near a piece of text to something in the lab, and he's zooming in on it by adjusting the scan pattern down to narrow regions. But he's doing this manually here. He's just very slowly adjusting DC voltages and frequencies and so forth to make this work. And that's not very efficient. So our most recent sort of line of work is to try to automate this process. And there are probably a lot of problems we'll have to deal with over this as in doing so. But some of the ones we've been looking at right now is that you can, if you're too abrupt about moving these systems, you can actually cause transient vibrations outside really what's safe for the actuator to move. Another one is this is where that cross-axis coupling between it really comes in. The frequency shifts not now just due to, say, environment, but you've got a fast axis running, you move your slow axis to a new position, and the fast axis dynamics have changed. And so we're looking at some ways to deal with this. One of the things we looked at was just an open loop. Can we design trajectories that are robust to transitions without breaking this pattern? This is what Hangji worked on. Essentially, you start out running your device at its initial centered on 0 and with its maximum range of motion. And then you want to move both its DC offset and its AC range into a specific region, which is less than the maximum portion. This gets into some other control techniques that have been used out there. I guess due to time, I won't get into that too much, but both open loop and closed loop methods used in previous micro devices. In this case, he decided on a scheme of just a very simplistic sort of set of step transitions to move from, say, 0 to the target DC offset, and basically then re-optimize these on 2 criteria. One was just a numerical study of reducing the worst case sort of overshoot, even if you don't know exactly the initial conditions, because we're not usually trying to synchronize this with knowing where we are in the scan pattern before this motion occurs. And then also with sort of minimizing the net voltage across the actuators as at least in the actuators he was working on, they were actually under constrained with 4 actuators for 3 degrees of freedom. And this was just numerical and simulation studies so far with real device models. There are trade-offs he finds between overshoot and the number of steps, but you can do some things like, this is some simulated motions where you can keep a pretty fast transient motion to the new scan pattern, where a direct step would have caused overshoot into an unsafe range potentially. He can smooth that out without losing too much total settling time. And then probably the more interesting one, oh no, this video keeps breaking on me. I just fixed it. But the E-Way has been looking at some of these actuators where the nonlinear coupling, where we push the actuator's motion even further with some designs. And the nonlinear coupling is terrible. So in my earlier pictures of scans, you have this nice rectangular Lysidue scan pattern. Here, he's just trying a raster scan. He's got one fast axis moving, and then he's slowly scanning the other axis back and forth. And you start out with a nice line, and then it quickly reduces down to almost nothing at the other extent of motion because the frequency at one DC offset in the other axis. So the fast axis is natural frequency at one position is very different from its natural frequency at the other position. And so the way this is traditionally handled in microsystems, or at least one really common way, is with something called a phase lock loop. You basically run your amplitude signal, drive it through the dynamics of the system, and then you compare a phase. You take the phase of the system, you measure the phase out, which we're pretty good at this point, and you compare it to the original phase of the system, and drive that phase towards some desired phase using a frequency controller, in this case, just a proportional gain, but there's variations you can do on this. And so we've just started to implement this. Okay, these are slides that I don't know why certain images on my slides just keep disappearing when I open and close this program. We finally, with the piezoelectric device, we do have some real estate for sensing. So what this was supposed to show, there's a small piezo resistor along these piezoelectric legs that's picking up the motion signal. And at least on the bench top, he just starts initiating the motion, runs it through the phase lock loop, and based on some arbitrary choice of nearby frequency, he's got a little bit of motion, and then running a phase lock loop, you can get to you drive it towards near its optimal frequency. This is what we call one of our wide field scanners. So that's actually quite large, about 80 degrees. This is just, nothing here is particularly special yet, except for actually the sensor implementation, integration. But there are some interesting questions I think that will arise in it. We will be wanting actually quite fast tracking of these frequency responses, which may require, and so how fast can the phase lock loop adapt? Can the phase lock loop by itself adapt as fast as the slow axis is moving, or do we need more sophisticated controllers here? Haven't even tried to make this reconcile with sort of transient motion controls yet. So these are sort of directions we're looking at these days. So I think in summary, really, probably I think of this as introducing some controls techniques that show up in microsystems engineering, or in other fields where they can be adapted to microsystems imaging engineering, such as image-based feedback for parameter estimation, self-sensing schemes, phase lock loop. And then there are just various minor twists different twists that come on them for the microendoscopy applications. Things like use of specialized filtering to do threshold detection and the phase delay detection. Certain image processing metrics work particularly well when you know what sort of scan patterns you're dealing with. And so those are basically what I was going to talk about in terms of control applications in this area. I'd like to thank very many students who have worked on this over the years, both in my group, mostly, and Tom's group, and now a number of other collaborators. I think we got support from the more images not showing up, but support from the NIH and SF mainly for this work. I'm happy to take a few questions. Yeah. Yeah.
Sorry.
Go ahead.
One simple question. What's the sampling time that you're running things?
So
Is it like microseconds?
So the image sampling time is actually 10 megahertz. In order to fill in all the pixels, you have to collect the intensity at megahertz range. The actuator sampling frequencies when we're trying to do control are typically in the 100 to 200 kilohertz range. But the actual updates of any control, like if we want to adjust phase or if we want to adjust amplitude, are actually quite a bit slower. We don't ever really try to do real-time feedback, closing the loop on the exact motion angle. Rather, we're adapting offsets and frequencies and at maybe 100 milliseconds sort of rate much slower. Yeah.
Thanks, Ken.
All right.
I kind of knew you were working on this, but I hadn't seen you talk in a long time.
No, I haven't talked in a long time, and I've never talked about the endoscopy work in the control seminar, which is why I chose to do it this time.
It's all the stuff that goes into a control application besides just designing an algorithm, which is usually the easy part.
Yes, I can ask you a question before.
Sure, yeah.
Yes, so, you were talking about how, one of the issues here is that the change in capacitance that you need to be able to sense is very small compared to other capacitances.
Yeah.
Have you, I mean, I'm not an expert in sensing hardware, but, I know that, you can get some mileage out of using, something like I guess a capacitor version of an instrumentation amplifier where you are able to amplify small differentials over somewhat high gains.
Yeah.
Have you,
So
is that what you're
that's
using?
basically already built into this. So you're actually taking a pretty small capacitance. You're already amplifying it. The bigger challenges are that the change in capacitance relative to the baseline capacitance is small.
Oh, I see. So you can't amplify one without the other.
Without the other. And then
I see.
the additional, you're basically amplifying the current draw that's going in and out of the capacitor.
Yeah.
And so you have a lot of that current draw going to the baseline capacitance on chip. We call that just the parasitic capacitance. And it's always present in these micro devices, and it can be, and it's once you add the transmission lines, it gets really bad. You're already driving this baseline. So again, we already use modulation techniques and stuff to try to minimize that, but that's one part. And then the other part is that your driving signal is capacitively coupled in, and it might be 40, 60 volts of drive signal. Your measurement signal might be in the millivolts sort of range.
Okay,
And so even if there's a small capacitive coupling between the two, it starts, if you don't do the modulation side of things, it really swamps the motion-based signal that you're trying to pull out. It's one of the it just happens all the time in microsystems. I don't see it necessarily as much in larger scale systems, but it's one of the fundamental problems you deal with all the time in our microscale actuators.
Well, thank Ken again.